welcome. We're going to go through the periodic table of currents. Okay, so using just the concept that there is a current entering into a polygon, I've been walking through the periodic table, and so I had this thought, so let me just go through it. I was like, can I just simplify how I draw this? So hydrogen. Let's just kind of start with, I guess, 1, 1. And just say, this one kind of has an in and an out. So I kind of drew it like that, almost. Like, it doesn't really... it doesn't really fit with the rest of what I'm going to draw like. So it has its own unique kind of thing. Maybe even just more simplified as like this. Like a zero, as a zero. Maybe as like the pixel in a way, like the base unit that repeat. Like, it's not the base unit, but it's our base unit of the periodic table. What, because it's like the one, because it's like a complete unit. Okay, where just an inlet comes in and there's no outlet. Okay, so I drew it kind of like this. Let's just go through maybe helium or hydrogen 2. We could draw something like this with like a dot. So this is my thoughts. Neutron is just a dot. Okay, so it's just hanging out there. Any line current is just the lines. Polygon is just the boundary that's not actually present. Like, so in this, for instance, here, there's a boundary. So I could draw that. So there's boundaries. But to just utterly simplify it, no, but I'm not even drawing the boundary. I'm just assuming the boundary. Okay. And we can do the same for you. Let's just do... with a dot on both sides. Essentially, it's like this. And this is where the vortex is. So then we move on to helium. And let's just start with 2, 3. Straight across. Dot. And I guess just that is okay if it's understood that this is just the basic, like, helium that also has 2 protons. Because if we just move on to helium-4 and just draw it as a straight across with a dot like that, now we're starting to get just like a structure of how we're drawing. Okay. Because if we go back to, now we're on lithium 6. grab this. So this current is coming across. There's a dot. There's two neutrons. One of them splits. Lithium 6. Okay, same thing, but not the same, because we know, sorry, not the same. We know, based on previous discussions, that it's likely that this doesn't split here, but instead, basically, it puts a support neutron here. So now, that's lithium 7. I'm not drawing the protons, I'm just ignoring the protons at this point, because I think that this is drawing the nodes and their positionings, and then the eddies and currents that flow within them can just be like deduced therefrom, perhaps. Okay. And just the fact that this is going to be really revealing as I keep going. From what I just did, I was like, what? Dude, it's like I kept doing this. So like, what happens next? Okay, well in this one, let's say this divides. So boron, or no, beryllium, sorry. Beryllium. That's how little I remember chemistry. As I teach you guys this. Here, let me share this with you. Boron. Isn't that like sodium hydroxide? In that there salt and pepper shaker. Okay. So then I drew, though. My thought is, let's just suppose that what would this do? This, if you were this current coming across, and you got this, like you're running in over here, and then you got like this back thing holding here, then you're just gonna do the same cut over here, right? You're just gonna cut across, and instead this time go up like this. Boom, 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 boom. Boom. 5 neutrons. So this is the key. 5 neutrons, stable particle. Okay, so I'm going to just keep putting in all of the stable isotopes. That's what I was doing. I was looking at what isotopes are actually stable. Okay. And let's just keep doing this. So just like here, it filled in behind it, so probably it would fill in behind it again. So let's say this one's boron. 5. Yeah. 511. So it adds a proton, which doesn't matter on this dot pattern. But it also adds a neutron, which kind of makes sense. Like if it's adding a proton, there's a good chance that it kind of stabilizes with this neutron involved. And now we have a nice little pattern that's interesting. So now it's kind of like, what happens? Does it like divide again? It doesn't make sense really to divide out here, because this current really just keeps going. And so it makes more sense that like this, one of these side currents kind of remerges with it and puts in another particle. So with that in mind, the next stable particle or atom is carbon 12 which has a sixth proton, so it's exactly the same neutron arrangement. Just this one has more current within the particle to a point where it essentially has another eddy. Another proton has like stabilized within the system. Mind you, all of these are having like polygonal shells still that maybe I was thinking, like, even though I'm drawing it like this, it may kind of branch out more like this and spiral around. Maybe even to a figure eight. I didn't really think to that point, but okay. So now, again, carbon. Same amount of protons, but now we're adding a neutron, which kind of makes sense here. Like, we're in this point where, like, another neutron could be added without adding an eddy, maybe. So we can just kind of do that segment there, keeping that, but now this current, instead of just trailing away, feeds back over because it runs into a new neutron that's there. That's basically causing another blockage in the path. And so we have now 7 neutrons, carbon 13, so it would make sense again to just throw another eddy in there and another current cutting back to essentially be again stable. Now this one is a short half-life, okay, which is going to come into play. It's going to come into play. This one, so let's just fill in that dot. This is interesting, right? Assuming this is happening, we have managed to like symmetrically arrive in the carbon region of all places at this kind of this pattern. Now, carbon 14 lasts 5,700 years half-life, has a 5,700 year half-life. And it decays into, are you ready for this? Nitrogen. Wait. 14. 14, yes. 14. Okay. So it's almost like this is not stable and one of these goes and becomes a proton, like an eddy forms instead and like blows out one of these. But it stably is held in position because essentially it's filling the place of the neutron. An eddy has removed the neutron's like bulk material and filled its space with an eddy that is a proton's current passing through, essentially. It's region where an eddy forms. Okay. Then the next stable one is again, though, back to this pattern. Stable. Okay, and then we go another proton up to oxygen, and look at that. These really critical elements have this like arrangement of their neutrons and eddies in ways that are all around this, basically this square structure here that may or may not be square depending on how, because essentially these are gonna probably fill outward in a way that changes the shape. Although maybe it is square, maybe it actually becomes square here in some way. Although oxygen, I'm not sure how this shape in oxygen, knowing how that its bonds are at like 104-degree angles, although maybe there's something in this. That would, like, the angle here that comes this way or something. But let's keep going. So then I said, well, what would happen next? It would probably begin to do the same thing, where it separates one of these distant neutrons and forms another one. So O17, same number of eddies, but it's just adding another mound in the arrangement of mounds that then forms on either side of the back here, depending on spin probably. Making then 9, and then we got oxygen. Let's get the last oxygen down here, which is just this side. Which kind of makes sense that it would be able to stably form another isotope by just adding like a symmetry to it without adding a eddy. So it's like this. I know it's kind of squeezed in there. I could probably add a few pixels here. Okay. So this one, even though it would probably be stable not with a new eddy, it would probably also be stable if it also formed with a new eddy. So let's go up to the only stable isotope of fluorine. Yep, 19, and just cross. Let's see if I can even do this. Splits once, comes back, splits once, comes back, splits, and then it just fills across here. Four, 8, 10, plus 9 eddies. So here we see maybe like this segment isn't really there, so it's more shaped maybe like this, and then just kind of like maybe like more like that. Okay, that's as far as I got. Now, next, let's see if we can keep going. Let's see. I put in periodic table of currents to see if anything came up. Neon. Okay. Neon. Isotopes. 3 stable isotopes. What were they? 20, 21, 22. Let's see. They're stable. Okay. Longest lived is 3 minutes for any other form of 24, which maybe we can keep that in mind. Neon. Okay, so we're seeing a logical thing that neon has a stable. We're just adding more eddies at this point. it doesn't really add new to this structure. So it just repeats. Maybe I can just draw it like that even. I don't know. It's kind of probably important to have the dots. Okay. But then it just adds two isotopes. So given this, it kind of makes sense that it would add one here and one here to kind of fill it out and be stable in those instances. So let's just say that's what's going on. And then we're through neon, dudes. And wait for it. This is neon. Oh. Coming in hot with that sort of filled neutron structuring. In a way, maybe it's balanced. Although there were other ones balanced. That one I misdrew. Uh-oh. How far back? No, what have I done? Okay. 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 Just the same, but this time with the full-blown window structure filled in. Maybe I should have put a little more time into that one. They're getting a little big. Okay. Then sodium has, let's see the isotopes. Isotopes of sodium. The only stable is sodium 23. So this base. That kind of makes sense. Like, if there were to be an only stable one that had a neutron arrangement from one of these neon arrangements, it makes sense it would be that one. So that fits. That's kind of one of the ways I'm kind of looking if this is making sense, like if it actually makes logical sense. Like, this would be the one that's most stable. So if there's only one. Okay, next one is, oh my god, I don't even know. Magnesium. Unbelievable. Uh-oh. Three stable isotopes. 24, 25, 26. Okay. $24. 25. 26. I just had this thought in case anyone doesn't know what I'm talking about and has somehow made it this far in these flows. I've been talking about this several videos now, so I'll just assume that anyone paying attention is aware of those videos. Okay, with that in mind, we add another proton here. So again, it's stable, just like over here, where this like symmetrical unit repeated 3 times. Like if it stayed around it, it's happening again here where neon, sodium, and also this one stabilizes at the same number of and shape of neutrons. And then it does the same thing, I'd imagine, where it probably comes out here and adds one like that. Now we're running into some interesting features where it's kind of like it probably comes out there and then out here. But then what? Like, does it come? It maybe comes down here and here. Then what? Maybe, I guess here. And here is like the optimal ones. It starts to become very interesting. Maybe it even branches off in ways I'm not accounting for. I should probably go back to the previous shape now. There we go. Okay. Maybe let's finish magnesium. And also notice it has 2 stable ones. So, like, again, it makes that kind of makes sense that it has 2 stable ones because of this. 1 and 2, like. Let's get this one here. Oops. Sure. Okay. Did I do that? And that one. Okay. So I'm thinking, like, in this instance, it doesn't have to split this one and put a new one here, in case anyone's forgotten what I'm doing. Like, I'm basically saying a current is splitting this one and moving it over. So it doesn't have to. It could feasibly put it over here. But then it's like out of balance, so it's not stable. These are stable isotopes. So, I don't know, just erase, but let's just go ahead. So it makes sense that it would have that one and that one as just another stable isotope. Okay. Do I keep going? It's kind of late. It's 2:30 in the morning. I'm just pretty excited that this is even working in like in a reasonable way, I think. Like, I honestly think it doesn't really make sense with like the whole picture, and like I haven't even thought about it, like electrons or where the proton eddies would be and all that kind of thing. But like this basic principle, maybe that I appear to be going through. It's only 27, and I don't like that it does that. Okay. So 26 can exist, but it's radioactive. Let's see what it decays into. produced from argon in the atmosphere. Aluminum isotopes have found practical. Okay, let's see if we can find. Its decay product is probably magnesium 26. Okay. Aluminum 26 decays into magnesium 26. Okay. But it's really only stable 27, so that's just, I guess this one. So if it's 26, then it would have to have this arrangement, which is probably why it's not very stable. And decays into, was it this one, the magnesium 26? It just turns into a neutron. That's right, I found it down here. Yeah. It just pretty much turns into a neutron. Let's just put that aluminum in there, because that one's just straight up another proton it's just intermixed in these mounds in a stable fashion. The mounds are directing the currents are flowing, producing eddies that are causing space between the mounds, allowing for the currents to flow, and the system just grows. And then there is silicon. Oh my god, I didn't say it right, so now I'm just going to say it wrong many times. Okay, 28, the most abundant. 29 is stable, and 30 is stable. Longest lived is 32, which has a half-life of 159 years. Okay, so let's start with 28, 29, 30. Okay, 28 makes sense because it, again, is like it's a pretty stable structure right there where it's got this 3 rows of 4 with a row of 2 behind it of the neutrons. So it makes sense that it would just stably add another eddy within there without like the system falling apart. So again, we just have the same structure. Did that one repeat 3 times? No. Yes. That one repeated 3 times, which again makes sense. It doesn't have to make sense, but it is making sense. That it is like stably repeating the same amount of neutrons where this like flow pattern across is vibrating towards. So just another neutron. So this one probably would form at the end here and start filling back in the back. So let's just say that, and there's 2 of them, which kind of makes sense, right? That there would be silicon isotope. Silicon? Oh my god. That word's always been, it's usually combined in so many ways that I don't even know the actual just base. Like silica. I feel like there's silicone. Okay. Let's add a proton or a neutron. So essentially, like this one divides. Or vice versa. I guess I've been doing the top ones first. Maybe I should keep it the same because it kind of probably is like spin based. At which point then we get 3 of these. Let's just count these. This should be 16, 12, 14, 16. We're good. We are good. The structure looks stable. Like something's like we're probably gonna see repeats of this 16 neutrons for the next 2 elements. Maybe even more once it starts. Now, who knows? Let's see. We'll find out. Phosphorus. Only 31. Is that this shape? No. It is. Like, it doesn't have to be, but it is. Okay. We're probably gonna see another one though. Like I need another one to be right, really, to see that there is some semblance of a pattern going on in that way. That's based on that. So isotopes of sulfur. Here we are. Sulfur. 4 are stable. 32, which is most of it. So most sulfur adds a proton to this structure, so it remains this structure, which is the most stable. It's hard to vibrate it out of. Think of it like that. Maybe that's probably a good way to it requires enough energy to start adding more neutrons, and it's pretty stable structure, so it really just as energy is added, instead it just forms more eddies within it until finally they can start to probably carve out to the top and bottom. That's my thought, is they go here or maybe here. It's hard to say. They probably add one there and then go there. Kind of just like pixels would do in a way. Let's see if the elements can like guide us. Chlorine. Two stable isotopes, 35, 37, mostly 35. Pretty good amount, 37. Interesting. Here we are at this what happens next moment, where it's kind of like, I guess I'll just go up there. Where this structure is very stable. And so it takes enough energy to break through this structure, but it doesn't just break through it. It goes up and it's a single proton, but to 35 and 37. So now we're getting to 20 neutrons. 18 for that one. So this one's got 16. So the next stable one adds 2. So maybe it adds 2 at the top and bottom. That kind of is suggestive because it goes up with 1 proton, but then up 2 neutrons. So odds are it goes like this. This. That center, just backbone, spine of the energy flow, and then the growth outward, which then probably splits this one to essentially produce like another one up there and another one down there. To again go back to a sort of, I'm not completely sure about that. It seems like it. I think the currents would do that. Like the path of least resistance would be at that point this way and this way. Plausible. And then if that's the case, well, let's at least draw this backbone again. And then the outer edge. So we got 17 protons, just eddies unaccounted for within these nodes of neutrons. 17, 18, 19, 20, 21, 22, 23, 27, 31, 33. So we need 4 more, like, neutron splits. And it may not be like this. Like, it may be that this system really would prefer to elongate and to split again here. And to split again here. And then to basically do this. And do like that. Honestly, I'm gonna just lean towards that those are the 2 vibrational balanced, like, energetic states of these arrangements that, like, can occur here, going from this one to the next one, and that both of them are pretty equally stable. This one may be a little more stable because it's more of the actual constituents. But let's see. Let's just keep going a little bit. I know I'm probably a little. it's a little early in the morning. Early in the morning. I mean, I'm about to be on Oregon, dudes. Okay, now I'm on Argon. Maybe 3 stable, 36, 38, and 40. Okay. 40 is most of that which is on Earth. Okay. 36, 38, and 40 are stable, though. Okay, so Argon. So we're going to see 36. So it's basically the same structure, just with another eddy in there of this one. I'll just draw it like that. To rush this up a little bit more, and maybe that's actually like there's got to be a shorthand that by just doing this we will arrive at some ancient languages, because they are talking about current flows in ways that are showing that, or this is 38. Was this actually enough? I guess I needed to draw these down here too. Okay, that makes more sense. 6, 12, 20, 20, okay. 20, okay, we're good. We are good. Argon. Let's keep going. Potassium. Isotopes. If I run out of the elements that I can recall, just know that I don't know anything. Okay. Okay. Too much in my head, everything just seeps out. It's like these. Anyway. 26 known isotopes, but this two stable forms are 39 and 41. Mostly 39. Okay. 39. And 41. So 39 is just another eddy in this one. Where at this point, I probably need to draw this. It really does help. Just to visualize it in terms of what energy flows would occur. Like to add 2, it almost has to, again, just add at the end here. Unless it's coming off of this one, can it add 5 off of this shape in like a feasible way? Maybe. It's possible. I think this is probably the more likely thing for it to do. There's gotta be a point, though, where it starts to branch out significantly to the side, and to basically to cause the shape to go back to more circular. Otherwise, I'm just going to keep going in a straight tube. Okay. I mean, this right here made it through. It actually provided like a reason for isotopes, for stable isotopes. This provided a reason for them. So it's gotta be, that's my thoughts. like this was too easy. Once the pattern was like deduced, it was just like overlaying it to the reality of the situation. Like, okay, this one has this many isotopes, okay, and just it adds a nucleus over here, adds a channel, then a nucleus divides, nucleus adds this back thing. Maybe I haven't been doing this. Like, maybe this happens more, like, back here. Or maybe it goes here, and then it happens, like, behind it, too. Like, here and here. Just start filling in, like, just some ideas. But, like, this, like, where it's stabilized, this one, that these shapes are stabilized around, like this one repeats 3 times, where this one does not. Which kind of makes sense. It would just go right through it. Okay, it had one stable one, but it didn't like sit on it. It sat on the stable ones, like this one. It repeats that one again and again, and then it moves past the unstable one to a new stable one, repeats it again and again, moves past that one to a new stable one, repeats it again and again, past that to a new stable one, repeats it again and again. And then we start to hit more complexities, but it's still doing the same thing where it's repeating this pattern, repeating this pattern, repeating this pattern. I think that's the same pattern. Repeating patterns. Yeah. This pattern repeated up here. Maybe I should add that one in. It's a little confusing since I didn't actually draw these, what I meant by these. This one must be this, though. Okay. We have the first 40 out 30 or no 19 elements. Sorry, 19 elements, 18 elements at least. I was gonna say 40, but that was the atomic weight, mass, weight. Oh, could you? Or is it? I don't even know anymore. Oh Lord. Okay, guys.